This is Paul Sanschagrin. I'm calling in from SB Grid. I'd just like to welcome everybody to today's seminar presented by Graeme on XIA2 for automated software for automated data reduction. I'd also like to mention, as you can see on the slide that's up now, we have another seminar coming up on May 16th on Eraser. And then you can see the other two on June 13th for Caber and July 11th for JALView. So Graeme got his first degree in mathematics and followed by a master's in mathematics, after which he joined the Medical Research Council Lab in Cambridge in the UK. As a software developer, he's worked on several software projects, including MOSFilm, was part of the DNA project, and is also part of the project for the eHTPX for high-throughput macromolecular crystallography. In 2006, he started developing the XIA2 that we'll talk about today. 2009, he finished his PhD at the University of Manchester, after which he moved to the Diamond Light source also in the UK, continuing on XIA2 development and some other software automation projects for macromolecular crystallography. So with that, I'd like to welcome Graeme to today's seminar, thank him for speaking, and go ahead and take it away.
Thank you very much. So this is a new experience for me doing a webinar. So if it's a bit shonky, then please excuse it. But it's a great opportunity, so thank you very much. Okay, so we have a slide here for systems check, which I believe is everything should be working fine. So I'll crack on. So I was asked to put a picture of myself on the introductory slide as well. Okay, so I thought I would start by introducing what XIA2 is, give you an idea of what it is if you're new to using the software, the kind of inputs and outputs you can use with it, some expectations you should have as a user. Then I was going to talk a bit about simple and more complex usage of the software package. Then I'm going to finish off with talking a bit about small molecule data processing, where the development of XIA2 is going, and finally some discussion on the sort of support of the software and references and so forth. Okay, so for those of you who don't know, XIA2 is an expert system for doing MX data analysis, but it uses existing software. So it uses MOSFilm, XDS, CCP4, and so on and so forth, and it uses them in essentially the same way as you would on your behalf. And the idea of it is that it can automatically reduce MX diffraction data from images through to reduced data, so structure factor amplitudes and intensities with little or no input from the user. Now, it was written originally to support the eHTPX project to allow remote operation of data processing. It is particularly useful to new users of MX who just want to use it as an analysis tool as part of their biology, but the tool itself is pretty much useful for everybody. I have a wide range of users. Okay, so what does it need? Well, as an SB Grid user, this is all sorted out for you by magic, but XIA2 does actually use a whole bunch of software, which, if you added it all up, is probably a couple of decades or several decades worth of effort from these people listed here. So I have to kind of acknowledge the fact that without the effort from all of these people here, there would be no XIA2, because it does run a lot of other people's software on your behalf. So acknowledgements to all of these people here. Okay, so one of the questions I was asked to answer is the typical instruments that are supported by XIA2 for data processing. So by and large, if you go to a fairly typical MX beamline pretty much anywhere in the world, I would hope that XIA2 would work with the data from that beamline. Equally, if you have any kind of fairly regular lab source at home, like a Rigaku or a MAR instrument, everything should work fine. The main exception to that is Bruker instruments, because they record their images uncorrected, and when you correct them, it loses the header information. So at the moment, there's no hope of processing Bruker data with XIA2. In terms of the kinds of experiments that are supported, pretty much anything you'll do in the macromolecular crystallography process. So MAD data collection, SAD, native, multipath, and to some extent multi-crystal. although that's ongoing work. Okay, so like any software, there are some limitations to XIA2. The first one I'll highlight is it is very dependent on having accurate information in the image headers. This is much less of a problem now than it was maybe 5 or 10 years ago. So by and large, you can normally ignore that. If there is a problem, then you can talk to Be My Scientist. Primarily, the software is limited by the quality of the data. So by way of a rule of thumb, if you can see spots and they look nice and round and well separated, then XIA2 should work. If you have horrible smudgy spots and they're overlapped and so on and so forth, then pretty much no data reduction software will work. By all means, you could give XIA2 a try, but there's a good chance it won't work. So it largely depends on the quality of the input. Okay, so to start a bit with talking about input, so the most simple usage, and I would say the most common usage of XIA2, is just simply to have a directory full of diffraction images, and you run XIA2 and you point it at that. That is pretty much the way I normally work XIA2. There are some command line options that you'll use on a day-to-day basis, which I'll cover in a moment. And there are options also to have the data, scattered around the disk and provide a XIA2 input file, which describes in a bit more detail what the data are, where they are, and how you want them to be processed. So I'm going to cover all of these things, but I would always suggest that you start with a simple way of running. In terms of the output of XIA2, then there's two main directories full of files. The first one is the data files directory that contains MTZ files and so on and so forth, and the log files directory, which contains the key log files that are worth inspecting. So I'll actually show those with some real examples rather than talking about them here. There's also a fair amount of output to the terminal and to the xia2.txt file, and I'll show that again with examples. Okay, so what you should expect as a user. So the automatic processing will by and large get the point group of the data right. So one of the common complaints I get from people is saying that, well, XIA2 didn't get the space group right because it's P43, not P41. Well, from the intensity data, it's impossible to tell the difference. Equally, if you have not recorded the axial reflections, it's very hard to even guess what the right space group is at all from the systematic absences because you haven't measured them. I would hope that the output resolution limits are fairly sensible. This is a classic conversation on the CC4 bulletin board as what's the right criteria for resolution limits. There are ways you can tweak how the resolution limits are decided as well. So there's a fair amount of control you have over it. It will cope with the reasonable amounts of pseudosymmetry. So if you have that archetypal case of an orthorhombic looking lattice that turned out to be monoclinic, it should catch that and process it appropriately. Okay, so I thought I would start with demonstrating a simple case of processing a boring data set. So I've got it's simple usage, so you just give it XIA2 minus 3D or minus 2D. I'll cover that in a moment. And you can either point it to an image, so it will simply process that sweep, or you can point it to a directory, in which case it will process every sweep it finds in that data set. If it finds only one wavelength of data, but it's got more than one sweep, then it will merge them together as if you've got a low and high dose paths or different kappa sweeps, for example. If there's different wavelengths of data, then it will process them separately, scale them together, but merge them separately in exactly the way you would expect from a data set. So there are 4 command line options that are used in almost every case. So specifying minus atom, which I'll discuss in a moment, and then minus 2D, minus 3D, or 3D II. So since these are used all the time, I thought I'd cover those in a bit of detail. So the minus atom X, where X is either letter X or SE for selenium or whatever, if you have more than one wavelength of data, then the anomalous pairs are separated by default. If you only have one wavelength, then the data treatment in scaling assumes the data are native, so you've got no anomalous signal unless you tell it otherwise. And the way you tell it otherwise is saying minus atom X, or whatever letter you want to put in there. If you have more than one wavelength and you specify a sensible atom, like minus atom SE or what have you, then if you have an edge scan file in the same directory as the data, the program will go away and run chooch and try and assign sensible names to the different wavelengths it finds in the directory. The other common option is the minus 2D and minus 3D and so forth. And this is essentially you telling the program which integration and scaling programs you want it to use. So MOSFilm uses 2D profile fitting, XDS uses 3D profile fitting, so minus 2D tells xia2 use MOSFilm and Scala, minus 3D tells xia2 to use XDS and XScale. Minus 3DII tells xia2 use XDS and XScale and also use spots from every image for auto-indexing. So this will actually find peaks on your entire data set. So if you've got a high resolution data set and lots of frames, that's going to take ages and not give you a better result. But if you've got low resolution data or small molecule data or very narrow sweeps, it is quite useful. Now that everybody has pixel array detectors everywhere as well, I'm finding more and more data sets consisting of several thousand images, and the default build of Scala tends to be limited to a small number of thousand frames. Aimless, on the other hand, does not have this limitation. So if you specify minus 2DA, minus 3DA, minus 3DAII, it behaves exactly the same way, except it uses aimless in place of Scala, and it has no limitations on the number of images you can have in a data set. So the biggest example I've processed to date is with 72,000 frames, and it processed fine, but it took absolutely ages. Okay, so I thought I'd start with a simple SAD dataset example. So this is actually data taken from a DNA crystal with a small molecule ligand in it. It's SAD data measured away from the peak, 900 0.2 degree images from a Pilatus measured at diamond here on beamline IO2. And quite frankly, this is excellent data. You've got a good on signal, high resolution, and it's just lovely. So the only command line I gave it is specifying xia2 to use XDS for processing. It tends to work well for fine sliced data, to separate anomalous pairs, and here's the directory with the data in. And so I'll just show you the output from that now. So in there, everything that is written to the console is also written to the xia2.txt file, so you don't need to worry about saving it, it's all there. So the beginning of this file is the kind of typical developer debugging stuff that I want to see to make sure everything's set up right. Surprisingly, showing the amount of free space in the directory is actually quite useful because xia2 can generate quite a lot of files, so it's useful to note there's lots of space. It also reports the command line used for processing, so if you come back later on and wonder how it was run, then you can see. So the first thing you'll see is that although we only have one sweep, it was indexed twice. So the first indexing is using Labelit, which has a pretty wide range search on things like the beam center and distance. So it does the first indexing and then it does a back transformation to figure out the most likely beam center and so on, which in the early days of xia2 made the whole system much more reliable. These days the beam centers are generally a bit better recorded, but even so, it's helpful to have that there. So the first indexing here is with Labelit. The second indexing is using XDS, but taking as input the refined values from Labelit. This is necessary because in indexing, XDS also refines the rotation axis and beam vector, and those need to be accurately determined before you begin integration. So after indexing, the data are integrated with XDS. And as anyone will ever know who's looked at a MOSFilm LP file or the XDS integrate.lp file, you'll get a very, very long report of how the processing went for 900 images. So in xia2, that long report is digested down to this block of characters you see here. And what that has is one character for each frame in the dataset and a legend below. So if you see all O's or mostly O's and a few percent signs like we have here, then by and large everything is fine. If you have data from a lab source and you see mostly percent signs, then pretty much everything's normally fine. If you have data from synchrotron and you've got all percent signs with exclamation points in there, then something is probably wrong, which might all be spotted later on. If you see capital O's for overloaded from CCD data and you still have the crystal, it may be worth going back and measuring a low dose sweep as well to fill in those low resolution reflections. And if you see full stops for blank images in there and you weren't expecting them, then there might be something wrong. For weak data, it might not be unusual to see all full stops because all of the images are weak. But if you see a chunk of full stops in the middle of the data set, it might be that your sample wasn't properly aligned or something like this, and it may be worth going back and looking at those images. So at the end of integration, some global post-refinement is done, and also some averaging of things like the reflection profile parameters. And so actually a better idea of what the input for integration should have been is available. So what XIA2 then does is actually run the integration again. And it does this because it slightly improves the quality of the measurements. It doesn't make a huge difference, and by and large, if you run XDS from just a single input file, it works quite well. But I did find that running it again tends to squeeze out a little bit more quality from the measurements. Again, yeah, the rest of the output is identical here. So after integration, the first thing it does is actually what it calls preparing for scaling. So this is going through each of the sweeps we've measured, in this case we've only got one, and making sure that when you analyze intensities with pointless, they are consistent with the Bravais lattice assigned for indexing and integration. At this stage, if you have a pseudosymmetric dataset, it will spot it and run right back to the beginning and reprocess it with a lower symmetry appropriate to the measurements. Here, everything was fine because it is actually tetragonal, so then it runs through a couple of cycles of scaling, after which the sensible resolution limit is determined from the scaled data, and then winds back again and rescales the data to that sensible resolution limit. After this, it has some further analysis with pointless based on the systematic absences and lists the likely space groups. So it will always select the space group with the lowest number that is consistent with the observed systematic absences. So here it's picked P41212. Obviously, if it's P43212, you can just re-index or reassign the space group in the empty dead file header later on. Then there is some description of the sweeps it's just processed and the table 1 information. So here you can see this is actually a fantastic crystal. We have lovely low resolution R mergers indicating that the strong data are exceedingly consistent. We have nicely complete data at the outer resolution shell, perfectly reasonable R mergers, and plenty of anomalous signal as indicated by the anomalous slope from the normal probability plot, the delta F over F, and the difference in the intensities divided through by the error in that difference. So by and large, there's plenty of information in here to complete your table 1 statistics. Obviously, for those of you who prefer RPIM or RMES, that's also reported here. Then at the end, there is a list of all of the relevant publications or citations for those programs that XIA2 has used. So if you use the output from XIA2 in a publication, then please include all of these references because they all contributed to your results you've got here. Okay, so as I was saying about the output, there for a single wavelength dataset, you'll get an MTZ file containing all of your intensities and amplitudes, and that can go straight into CCP4 or Phoenix. There's also data output in what's called unmerged scale pack format, so one file for each wavelength of data, and that's useful for input into shell XCD&E because it likes to be able to remerge the intensities itself. There's also a merged scale pack file, that used to be useful for lots of other programs, these days is not particularly useful, but I haven't gotten around to removing it yet. In the log files directory, you'll find a whole bunch of log files, which, depending on whether you use 2D or 3D, or whether you've got one wavelength data set or multiple sweeps and so forth, you may get more or less of these. But I would always suggest you take a look at the Scala log file and the truncate log file. So the first is to look for things like radiation damage and measures of the anomalous signal, and the second is to look for things like twinning. So let's go look at those. So to do this, I find the CCP4 log graph tool useful, and you just look at log files and then the name of the Scala log file. So if you look at the analysis against batches, this gives you the R merge as a function of batch, and this is a lovely example. You can see that's completely flat, so essentially there's no change in the sample from the beginning of the experiment to the end of the experiment. I have seen this little spike on the first frame a few times. I think it's from the partial reflections at the very beginning of the data set. If you look at the correlations within the data set, you get the CCI mean, which Phil Evans and Kai Diederich and several others would have you use to determine the resolution limit. So that's suggesting here that XIA2 is actually being a bit conservative. There's also a the correlation coefficients of the anomalous differences. So here you can see we've got strong anomalous differences out to about 1.5, 1.6 angstroms, so this is a fantastic data set. If we look at the truncate log file, then you get the fourth moment of E-plot that used to be quite useful for looking to see whether you've got twin data. So here it's exactly 2, so that's absolutely fine. With C-truncate, which is now run, you get some more sophisticated twinning tests. So here, as you see, that there's the observed and expected untwinned data. So it's absolutely bang on what you'd expect for untwinned data. So I think it's fair to assume that you've got no twinning. And also, if you look at the Wilson plot, you've got a nice flat Wilson plot, no ice rings, no problems in there, and a very good B factor for a maximum molecular crystal. Okay, so moving on, I'm possibly running a bit short on time, I suspect, so I'm not going to discuss XIA2 HTML, but if you run this after XIA2, it generates a nice HTML report which shows much of the same information but in a more browser-friendly manner. Okay, so although I said that running XIA2 from the simple way doesn't need any input files and what have you, what it actually does is generates its own input file. So it's called automatic.xinfo, and it expresses how the program understood your data set. So here, if it turned out that you did have some blank images in the middle of the data set, or you had you had a problem somewhere, you can adjust the range of images used here, or you can actually split this into 2 in order to show to remove some images. So I've got an example of that here, where I've taken that input file, I've modified it to remove 20 images from the middle. So I've then split a sweep 1 that goes from 1 to 450, and sweep 2 that goes from 471 to 900. Otherwise, everything else is unchanged, and all that will happen here is sweep 1 will be integrated, sweep 2 will be integrated, and then the 2 of them will be scaled together and merged. Okay. So, a more complex example, I thought I might cover a MAD dataset that's nicely radiation damaged from the JCSG. So this was measured a few years ago using a CCD detector, so it's back to the traditional 1 degree of frame, 3 90-degree wedges with the inflection and low energy remote measured first with 30-degree wedges, followed by the peak. This was run using pretty much the same command line as before, so XIA2 minus 3D minus atom X, blah, 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 blah. As there's more than one wavelength, minus atom is optional. If I had set it to SE and there was a scan in there, it would have run chooch, but I didn't. But I'm generally in the habit of specifying minus atom anyway. So let's take a look at the command line output and log files. So in the MAD directory, the output is very similar to what you saw before, except it's repeated for each sweep. So we've got 3 sweeps with 3 different wavelengths. So you've got the indexing and integration, more integration, and so on and so forth. Then when we get to the scaling, there's actually a bit more outlier rejection going on. So there's several cycles of scaling before it decides it's ready to go and figure out some resolution limits. And the first sign of having some radiation damage is here, that the 3rd sweep measured has a substantially lower resolution limit than the first 2. Once again, the same sort of output for the likely space groups. As it's MAD data, it also does some local scaling using Scale-It and gives you R factors between the first wavelength and second and first and third. And once again, we've got a sign here that there's something happened between here and here because the R factor's gone up by quite a bit. Taking a look at the table 1 statistics, we get perfectly reasonable R factors and so forth for the first sweep and second sweep, but if we look at the third, we've got, I say, lower resolution limits assigned, higher R factors here, higher overall R factor. So it's making a first hint there might be some radiation damage. If we look at the Scala log file, that suggestion of radiation damage becomes much more apparent. So looking at the analysis against batch for the first wavelength, so as I say, this was measured in 30-degree chunks, so that's the first 30 degrees, the second 30 degrees, and the third. And you can see that with the third 30-degree chunk, there's been fairly substantial increase in the R merge. If we look at the second wedge, the same thing is true, that you've got 30-degree chunk, and then a fairly big increase. So up to the first 60 degrees, we had a fairly nice R factor of about 5%, after which it increased quite a lot. If we look at the peak wavelength, which has disappeared for a moment, there we go, it actually starts at about 10% and increases horribly from there. So recalling this was measured afterwards, it's probably sensible to consider chopping off the dataset after the 60 degrees on the first and second wavelength. So in the same way as before, all I do is tweak the input file here. So instead of having 3 wavelengths like I've got here, I just remove any reference to wavelength 3 here and here. And where we have start end, just change those to 60. So we have that input file here. It's fairly self-explanatory when we actually look at them. So here we've just got 2 sweeps now. And if we look at how these are run, the only difference is now, instead of pointing at a directory to say where the data are, I point minus XINFO at my modified XINFO file. And we've got the same, exactly the same process going on here, where it does the integration twice, the indexing twice. We've got a slightly higher resolution limit assigned here, but more importantly, we've got much lower R factors everywhere, still pretty much complete data, and much more agreeable anomalous differences. So it does turn out these give you slightly better phasing statistics by throwing away some data. Okay, so I've just done what it said there. There are several command line options that you could find yourself using on a fairly regular basis. So if you know the space group and unit cell constants you want to process with, you can specify those through the command line. As I said just now, you can specify the location of an input file. You can process pointing at only one sweep, and also if you are processing only one sweep, you can give it the start and end for that sweep on the command line as well. So if you've taken one data set and the crystal died after so many frames, you can just process those few frames without writing an input file. You can also specify the resolution limit to use on the command line, but I would normally suggest that you either do it by modifying the criteria for the resolution limit, or you specify it on the input file if you've got more than one sweep or wavelength of data. Otherwise, things get a bit confused. There's a bunch of options you can set in the XIA2 input file, which are listed here. Some of them are relevant to the crystal as a whole, some to the sweep, some to the wavelength. These are detailed in the XIA2 manual that was included in the CCP4 newsletter a while back, but if you Google for it, you'll find it. Okay, there are some suggestions I would make for using XIA2 for small molecule data processing. So I would always use -3DII because you've got very few spots, so you need all of them for indexing. And I would also suggest you use the -small molecule command line option because this adjusts how the profiles are determined and it switches off the truncate procedure and so on and so forth. In many cases, it's also useful to specify -space group and -cell to give the program some idea, though I would warn you at this moment that XIA2 does not understand all these non-chiral space groups, so you just have to specify the right point group and then handle it a bit later on. Typically, small molecule data collection really pushes the geometry of the experiment much more than macromolecular work, so 2θ offsets and kappa goniometers and so forth. So you might find that it doesn't work for your experimental setup because they tend to be a bit more idiosyncratic. But I'm trying to develop it towards this a bit more. The next development areas for focus are primarily on multi-crystal data analysis and on improving the small molecule data processing. So the first of these has got to improve the handling of isomorphism and radiation damage and clustering and so forth. The idea being that if instead of data from one crystal you have in the directory data from 10 crystals or 20 crystals, the system should be able to work as it does currently and make some sensible suggestions on how to merge the data from all of those crystals. The situation for the small molecule data processing is a bit more procedural in the sense of extending it to cope with the different space groups and so forth, but it's still where some effort is needed. In terms of support for XIA2 users, I would always suggest that you take a look at the blog because that's where I write things that are happening with XIA2, where I publish releases, where I publish when there's known problems or issues with a new CCP4 release and so on and so forth. There is also a mailing list, which if you Google XIA2 mailing list, you'll find. That's got fairly low traffic and it's a great place to ask questions. If you find that XIA2 crashed, I will encourage you to contact the XIA2 support email address, which points to me, and attach some files. I'll discuss in a minute. That's actually listed at the top of the XIA2 program output as well. There's also a XIA2 manual, which you'll find if you Google for XIA2 manual, although the design of the software is such that hopefully you won't really need a manual. If you find that XIA2 does crash, it's really helpful if you can send those 3 files that are listed there. Basically what they say is what you were doing with the program, what the program was up to when it crashed, and whereabouts it did crash. So they don't really tell me a great deal about your data, but they do tell me a lot about where XIA2 went wrong. If you find that XIA2 does not work for the detector on the beamline you're using or for your lab source, then please do email me an image and I'll try and have a look at making XIA2 work for that. But there are some caveats that apply to that, so if the images are uncorrected, it's generally much more difficult to support. But as I say, for the majority of things like ADSC, Rayonics, and Pilatus detectors, everything works fine. Okay, so there was a XIA2 paper a few years back, which I saw was listed actually from the webinar advert page. That's also listed in the XIA2 output. But as I say, I would really appreciate it if XIA2 users, when you come to publish any results where XIA2 is used to reduce the data, it is very important that you include references for all of those programs that XIA2 has used on your behalf. So that's me done. I think I've been about 30 minutes as advertised, and I just leave you with the support information, and I'd welcome any questions. Thank you very much.
Thank you for the excellent presentation. If any of the people out there have questions, just chat them to me, and I'll pass them along. We did have one question come in that's how is the resolution limit determined post-scaling?
Okay, that would have been an excellent thing for me to cover. And, so essentially, by default, XIA2 will pick a resolution limit where your merged Iva sigma is about 2, and the unmerged Iva sigma is at least 1. It picks the lower of those two limits because if you have like 90-fold redundancy data, then it often happens that actually exceedingly weak data, when you merge all of those, gives you unreliable statistics. So that's where the unmerged Iva sigma comes from. The merged Iva sigma is just generally considered to be fairly reasonable. If you have different criteria, like you want to base it on the completeness or the R merge or the have different criteria for the merged and unmerged Iva sigma, you can set those through the command line. So if you set just minus I sigma and then some number, like 2 or 1 or 0.5 or whatever, that will be for the unmerged Iva sigma, minus mi sigma is for the merged Iva sigma. So if you like to have an Iva sigma in excess of 3 at the edge, then you can specify minus mi sigma 3. This is in the manual. Adding in the correlation coefficient-based resolution limit determination is on my to-do list, based on what Phil Evans and Kai Diederich and a few others say. So that should be done, but it isn't currently done. Does that answer your question?
If not, the user can go ahead and chat me again, and we'll try again. Sure. So another question came in that can XIA2 handle anomalous data from atoms other than selenium or only selenium?
Yeah. No, it will. XIA2, formally speaking, doesn't handle anomalous data at all. All it does is you say minus atom whatever, and it separates anomalous pairs. So if it's, I mean, the example I showed you earlier from that fantastic high-resolution data set was actually barium. But really, all you do is you say minus atom whatever, and it will separate the anomalous pairs. If you leave the edge scan in there and you specify a sensible atom name, so let's say you've done a mercury scan and you put minus atom Hg on the command line, it will go away and run chooch and specify the peak and inflection and so on and so forth. But there's no limitations at all on what data it can process in terms of any heavy atoms.
Okay, thank you.
Okay.
Another question came in that about plans or the possibility to go straight to auto-build from the output. Okay,
so way back when, in 2006, when I started developing XIA2, that was one of my plans, was to be able to run through straight from images through to automatic building and so on and so forth. But then, you know, the Phoenix guys have pretty much solved that. Tom Terwilliger with Solve and Resolve pretty much solved that too. So there's a lot of other people out there who've developed excellent software for going from reduced data through to electron density maps. So what I've tried to do as far as possible is leave the output MTZ file in a form where you can pick it up, throw it straight into the Phoenix Auto Sol or something like this, and it will just take it and run with it. And it should automatically generate you a map. I guess one thing which would be quite useful is if there's any additional information needed by Phoenix or any other downstream analysis that I could have generated, then I should be able to pass that along, which I guess I might be able to achieve. But I think focusing XIA2 on just the data reduction has helped XIA2 get on, and it also means that you're free to use one of these excellent tools that are out there for doing the automated structure solution.
Okay, thank you.
Yep.
Are there any more questions? Like I said, just chat them to me, and I'll go ahead and pass them along. Okay, seems like there aren't any questions. I'd like to thank Graeme again for the excellent webinar and the introduction to XIA2, and hope to see people next month for the seminar on Eraser. Thank you very much.
Well, thank you very much.
Oh, and I should mention, too, that this seminar is recorded, so if you'd like to come back to it, or if you have people who, colleagues or whatnot who are in the SB Grid who couldn't attend, that link was in the email. Thank you.